Okay, so today we are starting off on talking about probability distributions. And this chapter, obviously, we talked about its binomial distributions. Next chapter, we'll be talking about normal distributions. This one, well, let's just go ahead and go through this. This is from section 10.4. A probability distribution is a function that maps each outcome or event onto its probability. Rather than its relative frequency. The probability distribution is the theoretical estimation of chance for the experimental relative frequency distribution. So, just look at this. We have in way back in chapter 6, and by the way, you guys are going to probably want to go back and look at chapter 6 a little bit. Make sure you know the difference between permutation and combination for the quiz. Okay. This one says the 36 possible outcomes for tossing 2 dice are listed. If the dice are fair, then the probability of obtaining each possible sum is given in the table below. So the probability of tossing a 2 in dice. You have 1 chance out of 36, right? Because the only way you can get 2 is two ones. Okay? Probability of landing a 3. How many possible ways of getting that do you have? 2. A 2 and a 1 and a 1 and a 2, right? So there's only 2 out of 36 ways of doing that. Getting a 4, you have a 2 and a 2, a 3 and a 1, and a 1 and a 3. And
A 2 and a 2 again.
yeah, 2 and 2 again. So, but no, that doesn't count. So it's 3 out of 36, right? Okay, so anyway, that's how they came up with these probabilities, is that there's a total of 36 different combinations that you can make with 2 dice. And then the outcome, how many times that comes up in those combinations. Okay? So if you were to graph that probability, you're going to notice that it looks like this, where, 7 is the most probable of them. Okay. All right, so that is our first look at probability distribution. So a mean random variable. Why do we need a mean of random variable? In the calculation of a standard mean, all values are given equal weight. However, the mean of a random variable x is the weighted mean of a variable x, whose weights are the probabilities associated with each possible value of the variable. The critical difference is that not all the elements of the data set are not necessarily equally likely. And not necessarily given the same weight. Okay. Consider a lottery in which random 4-digit number is picked, pays out $8,000 to the winner. Okay, so it's a 4-digit number. We got 4 slots. How many possible digits are there? 10, right? 0 through 9 is 10 digits. So if I were to calculate all the possible combinations, there's 10 possibilities for the first slot, 10 second, 10 third, 10 fourth. Multiply that all out, I'm going to have 10,000 possible 4-digit numbers. Okay? So that being the case, then the probability of winning is what? Yeah, 1 over 10,000. Exactly. Or you could say it in this way, 0.0 0, 0, 1. Okay. Okay, so I'm going to make a little table here. We have winnings, and that's what I'm going to call that X. And I'm going to call this probability. Which you can think of as P of X, right? So if I have winnings of $0, what's the probability of getting $0? Maybe an easier way of thinking of this is what is the probability? Yes. What is the probability of getting $8,000? We just said that is what? 0.0001, correct? So what's the probability of getting $0? Yeah, 0.9999. Right? So if I'm going to I want to look at the unweighted mean. To calculate the unweighted mean, I'm actually going to take 0 plus 8,000 and divide it by 2. That would end up being 4,000, correct? But that doesn't quite seem right because you're much more likely not going to win. So you won't likely win $4,000, the more likelihood you're not going to win at all. So we want to look at a weighted mean instead. Okay? So I'm going to try to. So here's how you do the weighted mean. You're going to take 8,000. You're going to multiply it by its probability. So that would be 0.0001. And you're going to do the same thing with 0. 0 times its probability is 0.9999. You're going to end up with 80 cents. Okay? So this is like what you would get after the long term, long range. If you ended up buying around 10,000 tickets, you would maybe on average get 80 cents. Okay? On average, you would get 80 cents. So remember, this is a long-term calculation, okay? And we talked about after about, say, 10,000 tickets. Okay? So, 80 cents is the mean of random variable. Mean of random variable x. And we write that as x parenthesis mu. You guys remember that big old mu sign? I'm not talking cow moo, I'm talking about mu, okay? All right, so basically definition of the mean of random variable. Suppose x is a random variable whose probability distribution is x and the probability, x2 and the probability of x2, xn and the probability of xn. So the mean of this is adding up all of them multiplying each other. So what I'm saying is you're going to take 0 times its probability. You're going to take 8,000 times its probability. You're going to add all that together. Okay, so if you have a whole bunch of different possible winnings, you're going to take each winning times its probability to find this mu, okay? All right, so now let's look at example 1A. In the card game Bridge, a standard 52 card deck is used. The deck has 13 cards in each of 4 suits. In Bridge, the deck is distributed randomly among 4 players. Because certain cards beat other cards during the game, it is common for a Bridge player to evaluate 13 cards in a hand according to the following scheme. So an ace is worth 4 points, a king is worth 3 points, a queen is 2 points, jack 1 point, and all other cards 10 down to 2 is worth 0 points. For example, a hand with A, Q, jack, 10, and so on would be worth 9 points. Do you guys see why? Okay. So it says, A says, let X be a random variable standing for the number of points a card is worth. Make the table a probability distribution for X. Okay, so this is what it's going to look like. You're going to have X point value. And you're going to have P of X. That's the probability. Okay? We have several different possibilities. You have a point value of 0, of 1, of 2, of 3, and of 4. Okay? And there are 52 cards in a deck, so they're all going to be out of 52. Because it's out of 52. 52 is the denominator. Okay? So now, how many aces do we have in a deck? 4. So you have 4 out of 52 chances for that. How many kings do we have in a deck? 4.
I have a question.
Yes.
So would the 1, 2, 3, and 4 all be 4, and then 0 would be...
All the rest of it, the numbers 2 through 10 in a deck. Yep. So this one is going to be this is a ace, right? This is a king. This is a queen, and this is a jack. And this is numbers 2 through 10. So how many kings do we have? 4. How many queens do we have?
4.
And how many jacks do we have?
4.
Now, how many do we have for the rest of the deck?
2, 3, 4.
36? Yep. Okay, so that is our table for probability distribution. Okay, the next part says calculate the mean of the random variable x. So all we're going to do is take each point value times its probability. Okay, so we have 0 times 36 over 52.
0.
Which is 0. Good. And 1 times 4 out of 52 plus 2 times 4 out of 52 plus 3 times 4 out of 52 plus 4 times 4 out of 52. Okay? Now you can put this in your calculator and come up with a decimal. If you do that, you'll end up with about 0.769. So it says, what is the expected value of x? What exactly does this mean to us? Okay, this is saying the value you would expect for any chosen card over the long term, over the long run. So the value you would expect for any chosen card over the long run. Okay, so in this case, $0.769 is the value over the long run, even though there's not really any cards with this value.
Is that for B or C?
C.
Oh, no.
Okay. So this is, in this case, 0.769 is the value over the long run that you would get for any card, even though no cards actually have this value.
Wait,
what? Even though
We're taking the average over the long term, you know. Okay? So generally, on average, each card is worth 0.769 points. Okay? So, but in reality, there's not any card that has a value of 0.769 points. But over the long term, that's what it would be.
So are you just basically finding out what the average?
Long-term average. Yep, that's what we're looking at. Okay, so we're going to do this again, this time with 2 fair 6-sided dice. And they're tossed to let x be the sum of all the numbers in the faces. Okay? So you need to make a table with the probability distribution, just like we did in the last one. And then for part B, you're going to find the mean of random variable and see what would you expect the mean to be over of the long run. Okay, just like we did, but now you're talking about 2 dice. And I want you guys to take a minute and see if you can set it up by yourself. All right? Go. Okay, so basically to make this table, you can copy down this exact one right here. Same exact table from page 1. Okay? I'm not going to take the time to copy that right now, but you need that for this right here. Okay? Now, the next part says use the definition to find the mean. So you're going to take the sum of the values, which for number 2 is 2 times 1 out of 36. Yep. Plus 3 times 2 out of 36.
12 out of.
Okay, so make sure that you remember them when you're doing it, though, okay? Okay. So pause. So here it is. And guess what the answer to that is? How many of you actually calculated it? 7. 7 is right. Okay?
The other one was a decimal.
Yeah, this one just happened to turn out to be a full number. 7. So it's saying, what would you expect the mean of all the sums you toss over the long run be? 7. That would be the mean over the long run. Okay? All right, so let's turn the page. Yep, there's more.
Wait, what did it equal?
7. Variance and standard deviation of a random variable. Recall that the variance, sigma squared, and that's a little sigma, of a population is the average squared deviation of the members of the data set from the mean. Okay? So in our case, the variance of a random variable, sigma squared, so the variance is taking each one minusing the mu that we found a few minutes ago and then timesing it by its probability, okay? So the standard variation of a random variable is the square root.
What's the symbol that looks like an upside down Q?
This right here?
Yeah.
That's sigma. It's a baby sigma. It's got 1 hair on its head. So you could think of it as baby. Okay? Or sigma. Okay, so a charity holds a raffle. The tickets are $10 and all 1,000 tickets are expected to be sold. The first prize is, sorry, I see that now, it's a typo, is a $2,000 TV set, and there are 4 second prizes and 10 third prizes are worth $100 each. If you buy a ticket, what is the expected value of your winnings? Okay, so the first prize is $2,000, right? So 2,000, and what's the probability of drawing a $2,000 prize? 1 over 1,000. Okay, plus the second prize is 500. So what is the probability of drawing a 500? 4 over 1,000, yep. And then the third prize was $100, right?
So 100 times 10 over 1,000.
10 over 1,000, correct. Okay? So, and then what is the possibility of getting no prize?
999.
Yeah. So you're going to add these, so that we got 1 plus 4 plus 10, that's 14, right? And subtract that from 1,000. Oops, 15, sorry. 15. Subtracted from 1,000, which is what? 985 over 1,000. Okay?
Do you really have to do that?
Yeah, why?
It's going to end up being 0. Yep.
But why do we have to add that?
Well, all your one of the things that you could do when you're checking your work.
Zero, you have a 0%
Oh.
chance of winning?
No, sorry, I was looking at this.
Okay.
Why do you have to add the zero?
You're not gonna win.
100% chance.
Okay. So anyway, it should be 5. It adds up to be 5. Okay? So on average, what this means is on average the charity earns $5 for each ticket they sold because they sold them for 10. Okay? So you might want to write that. On average, yeah, nope, this is still for A. The charity earns $5 for each ticket sold. I can't write today. Oh, what's new? Because they were sold for $10. Okay? All right. Part B. Part B says, what is the variance and standard deviation of the random variable in this situation? So there's quite a bit that we need to write down, you guys. We're going to make a little chart. I know, right? You guys love charts. So prize, which is X, is our first column. Okay? The probability of X is our second column. Okay, our squared deviation, so that's that little sigma squared, which happens to equal X minus mu squared. That's a sigma. It's a little baby sigma squared. Okay?
What's the difference between a baby sigma and
A big sigma looks like this.
what's the difference?
This one's usually used for standard deviation or variation. This one's using for summing, adding up things. Yes?
The little thing is about $5
Yes. That will be $5 in this case. This happens to equal mu, right?
Should we just write 5?
Yeah, you can. So, hold on. I'm almost done. Oh, deviation. Yep. Times the probability. Okay. So our first prize was what? 2,000. Okay. Our probability for getting first prize was 0.001 if I put that in decimal form. Okay. So our squared deviation is going to be 2,000 minus 5, which we found up here, squared, which happens to be what? 1995 squared.
We don't need to figure out it Oxford.
Not yet. So our deviation in this case is going to be 1995 squared times 0.001. Does that make sense? Okay, so what do you think would be the next line if it's $500 prize? Yep, 0.004. What's our deviation here?
595.
Yep. Squared. Okay, and that ends up being 495 squared. Okay, and our deviation times our probability? Yep. Okay. We got 2 more to figure out.
How are you getting the P of X?
Because we found it up here, the probability of drawing, because they sold 1,000 tickets.
Oh, okay.
Okay? Good question. $100 prize.
0.01.
0.01 or 0.010 if you think about 10 out of 1,000. Okay? So 100 minus 5 squared is the same thing as saying 95 squared. And then 95 squared times 0.010. Then the last prize. What was our last prize? 0. Okay? And we had, in this case, it's going to be 0.985.
What would the next one be? Just like -5?
Yeah, right. It's going to be 0 minus 5 squared, which happens to equal -5 squared, like this, correct? Okay? So -5 squared, does that end up being a positive or a negative? Positive, because a negative times a negative is positive. Times 0.985. Okay? So if you were to add all these up in the last column into your calculator, you would end up having 5,075.01 equaling to the little sigma squared.
5,000.
5,075.01.
And that's what they made.
Mm-hmm. All right. Okay, so if that's the case, what do you think the standard deviation is, if this is the variation? You square root it, yep. So if I just take this, if I take the square root of that, you end up with, yep. So 71.24 is what I ended up putting down. I think I rounded it up.
That's how much it's making each ticket.
No, this is a variation. The other one was making $5 a ticket. It's when you were looking at the mean winnings. Okay? All right. So that is really it for my lesson today. You guys can work on the assignment, and the assignment being, I will pull that up for you. Hold on a second.